Thank you, Professor Lee,
Okay, can I start my Q? Oh,
for
yeah,
the
sorry.
very interesting session. Um, yeah, you can start with the Q&A box if you wish.
Okay, so there are almost 10 questions in the Q&A box. And then the first one, how can I pursue my MP degree in this area of chemistry? Well, this is a very basic question. You need to find where you can enter, which university you can enter, and you need to get the admission, and then you need to contact the professor you are interested in. So that's the very common process. And also, kindly tell me about the software which you have used for the MC Monte Carlo simulation, DFT simulation. Well, so the Monte Carlo simulation, we use R. The software name is R, which is the free software. And that is the typically used for the data mining and the machine learning, the scientist. And for this, we already published how you can build up the Monte Carlo simulation, the process in the chemistry material as a method format. You can read that article and you can follow. We already uploaded the software file in the website. You can download it and you can try to on your computer. And tell me something about isophobicity. Well, isophobicity was not the topic for this talk, but to briefly explain, well, we used the superhydrophobic surface coating for the ice. Superhydrophobic coating means the low surface energy, and then water adhesion force on the surface is very small. Because of that, ice adhesion force on the surface is very small, and then we can easily detach. We can eliminate the ice from the surface. Okay, so is it possible to design a nanomaterial and to incorporate into a chip and then to absorb the greenhouse gases? Well, I never thought about that, but to solve the greenhouse effect, we have to reduce the carbon dioxide, the carbon monoxide, the mainly carbon dioxide. So if you synthesize any material to efficiently absorb the carbon dioxide, you can solve that problem. Okay, so that is not my main research field. So the question is, what's the some change one may expect to encounter these metal nanoparticle are loaded captive biomolecules such as well, this is not directly related to my talk and my research field. We can skip these things. Can interstices from the doped ion disrupt some reaction in ALS? What ALS? Wait, what ALS
It's
means?
actually ALD, Professor Lee, and
Oh, okay.
interstices means defects, interstitial defects of the solid state, basically.
Well, that's probably impossible because the ALD reaction is taking place on the surface. If the surface there are some dopant or impurity on the surface or doped elements right on the surface, probably the reaction could be changing. So how do the mechanism of the light absorbance and acid generation differ from the EUV ridges compared to the previously generated chemical amplified ridges? Okay, so that's a really important question, but the dry PL technology, it's some kind of confidential technology for their industry, but they didn't officially announce what's the material for the dry PL. But based on the literature, that dry PL is the tin oxide, and once tin oxide exposed to the EUV, the phase was changed, and then there are development to selectively remove the specific phase of the tin oxide. So this is the different from the organic PL. So can ALD be used for the substrate apart from silicon? Well, my understanding is, can ALD use for the other application or the other substrate? Well, that's possible. So I'm only talking about ALD for the silicon device fabrication, but ALD is now applied for a lot of the different type of application. For example, can be used for solar cell, battery, or fuel cell, or bioengineering, or sometimes some researchers try to deposit ALD film on steel for the car fabrication, car making, to protect something. So ALD is just kind of, you can just think about ALD thin film deposition tool, but the fabrication cost for the ALD is much higher than the other thin film deposition techniques. So you have to keep in your mind, ALD can deposit something, but the problem is price always. So what should be the basic element to start the silicon research? Well, basic elements like basic class or basic knowledge. So silicon research means like a semiconductor research. You have to take the very basic modern physics and a solid state physics and a silicon device physics and a surface science and a vacuum, something like that. So that's the important class for that. So ALD TiO2 is crystalline or amorphous. It depends on the deposition temperature. If you deposit TiO2 at low temperature around 100 degrees C or 150 degrees C, it's going to be amorphous. But over 250 degrees C, the crystalline phase is anatase, or over 300 degrees C is going to be luteal. And so what's the biggest tech limit to three-dimensional manufacturing? There are tons of challenges to fabricate three-dimensional manufacturing. But basically, right now, the most important thing is, well, we are now trying to make EUV. We can keep EUV for below 2 nanometer or 1 nanometer. But think about that. The atomic typical size of atoms is around angstrom. So we almost going down to one single atom size. So that's the important thing. And then to overcome that issue, we have to keep performance, keep maintaining the performance silicon chip. So for example, M2 Ultra is the two chips are connected with each other. So interconnect between the two different chips is getting important. So in your opinion, do you think direct write techniques such as direct atomic layer deposition can be significant for competition traditional? Well, direct writing, selective deposition is some kind of the direct writing technology. But the important thing is selective deposition, one of the solution to overcome that problem, like photolithography problem. But there are other like candidate, but most of the researcher in the semiconductor industry, they trust the selective deposition is the strong, like most possible candidate to overcome that. So as I explained, the researcher in the semiconductor industry, they don't want to change a lot. They just want to use just the things they already use. So that can be really the great solution for the future. And then that's the reason I'm studying the area selective deposition a lot. How could you control the layer thickness? As I explained in the ALD growth mechanism, we can control number of ALD cycle to control the thickness. How much cost came nano device verification by ALD process? Well, I cannot understand. I couldn't fully understand what's the meaning of the question, but well, it's not very cheap, but well, it depends on the material and the process. And then, but you know, for example, like a DRAM device, DRAM memory fabrication, so we have to decrease down the fabrication cost in a specific amount. but the logic devices is going to be very expensive. So for the ASD-based patterning, the CD, critical dimension, depends on the pre-pattern resolution. What CD can be reached by the DSA for the pattern? Well, that's true. Well, basically, the pre-pattern can be obtained by photolithography technology. And then also, as I explained it, the pattern fabricated by photolithography process can be reduced more by using double patterning technology. And then we can combine the selective deposition for more. And also, by using the selective deposition, so, well, I have communicated a lot of the person from the industry, but they just keep focused on, they can simplify their process. They can reduce cost down their fabrication cost. That is the one of the important purpose to adopt the ASD for their research. So thank you for the talk. What's the maximum size of the deposition area for the ALD? Does the scale of the deposition area increase the cost linearly, exponentially? What's the increase of the layer thickening? Well, almost the 12 years ago, so the protection layer for the OLED device, because that is organic display devices, we have to use some protection barrier from the moisture. So they use the ALD aluminum oxide, and then the device, like substrate size is 2 meter by 3 meter. It's a very large. And also car making and steel making company, they trying to consider the ALD for the protection layer on their steel, and that is over 10 meter. That is very large. And then, yeah, that's the, what kind of the fabrication technology did the China SAM use in latest chip? I don't know the technological node for that, but basically the fabrication technology are same in China, because that was developed from the Western country, and we developed a lot. So that is the basic, fabrication technology are same. Probably around the 10 nanometer. I'm not really sure, but you have to keep in your mind, if a company really announced they finally achieved the 3 nanometer technology, but the problem is yield. If they have the 3 nanometer technology, but yield is like 20%, that cannot be used for the mass production. You do not believe the newspaper. How does the use of the sequential wafer surface? I have a question. Do we have the time limit?
Yeah, I was just going to ask that, as you can see, the
Okay.
audience members are still there. So maybe you can take a few last question, and then we can close the session.
Okay. Let's finalize. Let's try to answer the one more question. And if you have any question, just email me, please. Thank you. How does the use of the sequential wafer surface reaction in atomic layer deposition contribute to the precise control of the thin film deposition? Well, as I explained, ALD film is formed through the surface reaction, precursor and a counter reactant sequentially. So we can very easily control the thickness. But the thing is, the secret in the ALD growth rate is not over one single layer of one single atomic layer, because that is always the growth rate is always smaller than one atomic layer, because of like static hindrance effect or any other complicated chemical reaction. So if you are interested in that, I can recommend some of the review paper for that. You can study. Okay, so this is going to be the last question to answer. Thank you.
So, thank you, Professor Lee. Do you have any, would you like to leave our audience with any final remarks, broader remarks?
Well, yeah, I mean, so there are many great attendees and a great audience and a great question. So it was a real bit sad to meet in person. I couldn't meet in person, but I think I have a really great time. And then because I'm super fundamental oriented scientist, but because I'm an engineer, so I have to remember how can we apply our knowledge for the final product, and a final product can make all humans very happy. So I'm always thinking about the possibility of my technology for the real final product. So if you are engineer, you always thinking about that. That is the one of the great way to promote your technology for more. Thank you.
Thank you so much, Professor Lee. I think the wonderful passing remark. With that, this brings us to the end of today's session. We hope all the audience members that you have been here have enjoyed this broadcast. We invite you to view the edited recordings for the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. My colleague might have posted the survey link in the chat as well. So please do give us your feedback so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy.
Thank you.
Bye, everyone. Thank you.
Bye-bye. Bye-bye.